Andres Urbina. He's from Eslichenko group from Purdue University. The floor is yours, Andres. Then can you, I know listen to you, can you share your screen? Yes.
Yeah, I'm sharing my screen right now.
Okay.
Can you see the slides?
Yes.
Okay.
Okay.
I'm ready then. Okay, so thank you, the organizers, for this opportunity to present my research. So today I'm gonna talk to you about workflow we have developed in the Eslichenko group to study protein ligand interactions using the effective fragment potential method. And specifically, I will give an example of GPCR-Ligand complex that we have some preliminary data on. Let me first get started with the effective fragment potential method, EFP. So the effective fragment potential method is a fragment-based, it's an ab initio fragment-based polarizable force field. The parameters of these fragments are obtained from ab initio calculations. And in theory, this method can be applicable to any solvent or environment. And but by using this method, we can gain some physical insight on the composition of molecular interactions. This can be used as polarizable embedding, so it is included in the polarizable QM-EFP models. So the EFP interaction energy is the sum of the electrostatic energy, polarization energy, dispersion energy, and exchange repulsion energy. So that's all the terms that are going to be in this interaction energy. And as I mentioned before, you can have these fragments interacting with a quantum region. If you're more interested in the EFP method, these are the relevant references. So feel free to look at them. Now I'm going to talk a little bit about the EFP fragment setup. How does EFP work? So we have to prepare these EFP fragment files. So here I'm showing an example of a simple molecule that we're all familiar with, which is water. So when we run our EFP calculations, we'll get parameters that will correspond to multipoles that are associated with the electrostatic part of the energy. And these multipoles consist of monopoles, dipoles, quadrupoles, and octupoles. And these points will be placed in the position of the atoms and also in the midpoints between them. We also have the centroids that are calculated, which are associated with the local molecular orbitals. And these centroids that are shown in the next figure on the right, there's a centroid per bond and per lone pair, and these centroids correspond to the static polarizability tensor and the dynamic polarizability tensors. So other parameters, we also get wave function and the Fock matrix, which will allow us to calculate the exchange repulsion term. How do we run these EFP calculations? This is part of games, so you just need to use this ab initio you just run this ab initio calculation on games, and in principle you can do any fragment. So far we have explored different solvents and amino acids to explore macromolecules, specifically protein. And what is nice about EFP is that you can have a database of fragments that can be used for different systems of interest. Once you have your EFP files, what can you do? You can calculate EFP interactions by semi-classical formulas. You can calculate QM EFP interactions via one electron terms in QM Hamiltonian. Specifically, you could do SP calculation, single point calculations, geometry optimizations, molecular dynamics, Monte Carlo, and all these could be done in games QChem, Cipher, or LibVFP, which is a software that we developed in our group. Okay, so where has the EFP method been applied to? So the first generation of EFP called EFP1 was applied first just to study water cluster and hydrated solids, and specifically was used to study photochemistry, and it gave very good results. EFP1 didn't include dispersion and exchange repulsion separately, so those two terms were developed afterwards, and that's when those terms were developed, that gave rise to what is called the EFP general model, or EFP2, which is the method that we are using in the Slipchenko group. With EFP2, we could extend our studies to other type of solvent environments. Now we could study different molecular clusters and liquids. And in the Slipchenko group, we are trying to use it to study proteins and macromolecules. And specifically, we have these two applications called BioEFP and Flexible EFP that allow us to study polymers and proteins. If you are more interested in how we do it, feel free to look at these references. Okay, so recently we explored, we wanted to tackle a excitonic model. So we, in our group, we studied the Fena-Matthew also complex, and we applied multi-scale modeling with effective fragment potential method. And in our group, we were able to get results that are comparable to experiments, both for the absorption spectra and the circular decoy spectra. So this is just showing like the power of these type of simulations. So QMEFP was able to reproduce these experimental measurements. Okay. Now let's talk a little bit about my project and what I wanted to share with you today. So today I will be showing with you my work in GPCR-Ligand interaction. So I want to give a brief overview why these proteins are important. So GPCRs, or G protein coupled receptors, are cell membranes, and they are very important because they are associated with most of the physiological responses that happen in our bodies. Interestingly, these GPCRs have unique combinations of signal transduction activities, and they are associated with different diseases. Approximately 50% of all drug targets are developed for GPCRs, and surprisingly, these drugs only target around 50 of the 800 known GPCRs. So what are we trying to do here? We are trying to guide drug discovery by understanding the structure-activity relationship and understanding the interactions between the protein and the ligand. Here, I'm just giving an example of signal transduction pathway or of type 2 beta adrenergic receptor. So the protein, the GPCR protein, I don't know if you see my mouse, is this pink protein here, these two guys here. So this is the G protein receptor. These are the G proteins. So as you can observe, these arrows are all the biological responses associated with these GPCRs. So this is why it's important to study how these association with ligands affect this. Here I want to mention that the ligand can, depending on the ligand interaction with the protein, the biological response can be different. So if the biological response is kept, that ligand is called a full agonist. if that biological response is decreased, that ligand is called a partial agonist. If the ligand keeps the biological, if the ligand changes the biological response or suppresses it, it's called an inverse agonist. Okay, a little bit of structure-based drug design. So what we want, we're trying to optimize interactions between ligands and proteins. Right now, this process relies on the information from the geometry that comes from X-ray crystal structures and affinity interactions that depend on the force fields used for MD simulations. There are other interactions that are not included in force fields. So that's why it's important to include ab initio fragment-based approaches, because this can give us key information about the interactions between proteins and ligands. In this regard, I want to mention that there's pioneering work that have explored ab initio fragment-based approaches using the fragment molecular orbital method that has already been used to study interaction energies between protein and ligands, specifically pair interaction energies. So I will refer to this work to compare some of my results too. Okay, now let me talk a little bit more of the system I studied. So I studied the beta-1 AR carmatoral complex shown here. So it is a dimer that has this PDB ID. Each subunit contains one ligand and 325 amino acids. And the ligand in this particular case is carmatoral, which is a full agonist. And the 2D structure is shown here, and you can hope you can, it's not too difficult to see it, but the ligands are shown also there in the protein pockets. Okay, now I will guide you on what I'm doing with the molecular simulations. So first, I start with a classical simulation. In particular, for this system, for the protein, I use the charm 36 force field. For the ligand, I use the charm generalized force field. Water, I'm using the TIP through P. And for these preliminary results, I just did an energy minimization. And for all this work, I use GROMACS. Now, the next steps will show us how to prepare a system from a geometry input file of any MD simulation to prepare it for an input file that could run an EFP calculation. So the first step, or here it is step 2, which is just a system reduction. What it does, we use this Python script called cut water 50 angstrom. And what it does, it's just gonna cut all the waters that are beyond 50 angstroms around the protein. And here is just how it works. So we just give it a geometry file as an input. As an output, it will give out, it will return another geometry file with the excluding the waters excluding the waters that are not within this 15 angstroms. Now the next step is to find the EFP region. So for that, we also developed a Python script. So for this step, we need the first G96 file generated in step 1. We also need to know like a cutoff of interest. In this particular case, our cutoff was 4 angstroms. And also we need to know the res index of our, in this case, our ligand, but this could work for any residue. This case is our ligand. And then the output will be another geometry file, a G96 file that will have all the residues within 4 angstroms of this ligand. So here in this Python script, we basically call GROMACS, and here is And with GROMACS, we use the select function and the trajectory conversion function just to obtain this this geometry file with these residues. Okay, now the next step. So once we know our EFP region, what we do is we have to fragment if we have a polypeptide chain, we have to fragment that chain. For that, we use a Python script called make EFP fragments. And here, for input files, we will need our step 2 G96 and our step 3 G96. We also need the charges of from the molecular dynamics from the topology files. So here we have to add them to what I call this is just a text file with all the information of the charges of the system. I just call it a super ITP. So the input files are all these three, and then the output will give us all the fragments in EFP format, as well as a super fragment that include the region that is not in the EFP region. So whatever is beyond the EFP region. Also it is important here, also in EFP format. So how do we cut this polypeptide chain? So basically we make the cut between the carbon and the alpha carbon, and we cap it with hydrogen atoms. So at the end we have a closed shell molecule like this. We calculate our EFP. We do EFP calculations on these residues in step 4. Using from step 4, and then we use gains, and these frag input files then will give us now the frag EFP files that are the fragment files for the amino acid fragments that are capped. Then the next step is, since we introduced these hydrogen atoms, the next step is to remove these capped hydrogen atoms from these residues. So for that, we also generated our own Python script. So this Python script needs all the fragment EFP files, and the output will be the same fragment EFP files without these capped hydrogen atoms and without any parameters associated with them. So we will get something like this. Next, we use another script that is called make EFP input that will just search for all the EFP files that we have in our directory, and it will just create an output that is called, in this case, it's called sp pairwise.imp, that it is ready to run with EFP. And the last step is step 8, which is just doing the live EFP calculation that allow us to, that we're using now to do SP calculation and to calculate pairwise interaction energies. So in this figure, I just want to show you that here, where I'm showing you all the fragments that are included in the EFP region, and also the super fragment that are basically just they're just basically monopoles, and it's part of our MM region in these calculations. I want to go back a little to this step just to mention that step 4, step 5, and step 6 is part of what some of the work we have done before in our group, and it's called just BOEFP fragmentation. Just references to the way we're cutting the polypeptide chain. Also, I want to mention that there's this other application called flexible EFP that will skip step 5 and step 6 if you have a database of fragments. And basically what you will do is you calculate your fragment, you will see how different it is. No, you will get your fragment, and then you will go find it in a database, see how different it is. If it's not very different based on the RMSD, you can basically use that EFP file from that database. So this is just letting you know that you can play also with this with a database, and you don't have to calculate EFP fragment files if you have access to them. Okay, now I want to mention like just an overview of all the steps I did and all the scripts and software I use. So first I did the first step is the classical simulation, followed by step 2, which is system reduction. Then step 3 is finding the EFP region. Step 4 is EFP fragment construction. Step 5 is calculation of capped fragments. Step 6, removal of these capping atoms and associated parameters. Then step 7 is building the EFP input file, and step 8 is just the calculation. All these scripts, we will make them available in the EFP2 GitHub account. So yeah, we will eventually post them there once we validate that they work correctly. Okay, so now let me show you some of the results we got for this particular example. So for the beta 1 AR carbonatorial complex, we calculated pairwise interaction energies. So here I'm just showing you the 10 amino acids that have the strongest pairwise interaction energies with the ligand carbonatorial. So here you can observe that aspartame 121 located here is the ligand that is the amino acid that is interacting more, or with the ligand. And yeah, this is the information that we get. What is interesting is that there's crystal water that it's also included in these results. Now I want to show you the composition of energies that we also get from these pairwise interaction energies. So here we can decompose the interaction energies in electrostatic, polarization, dispersion, and exchange repulsion. It's interesting that, as I mentioned, that water that is also part of this set of molecules that are interacting strongly with the ligand has a big exchange repulsion. And yeah, different information that you can get from these type of simulations. Now, as I mentioned, there was a previous work done using the fragment molecular orbital method. So here I'm just showing you the amino acids that we both observed that had the stronger interaction energies with this particular ligand. So you can observe that our EFP method compares reasonably well with our fragment with FMO method, and yeah, like we can say that EFP can be used to do this type of analysis. Now, I would like to conclude this talk and tell you what we're going to do next. So I show you that we have developed a workflow that allows the investigation of the interactions of protein ligand complexes using the EFP method. This protocol uses open source software, GROMACS, games, libEFP, and Python scripts. We are planning to investigate more GPCR structures containing agonist and antagonist ligands to explore different interaction patterns. And we will also explore large range effects, dynamic effects, solvent effects, and we will benchmark these EFP calculations with SAP pairwise interaction energies as well. With that, I will conclude. And I'll just want to thank my group, the Zlipchenko group, Dr. Yongbin Kim, with helps with some of the Python scripts, and the Department of Energy and the NSF for funding. And I can take questions if we have time. Thank you.
Thank you so much. I really enjoyed your talk. So many memories about GPCR receptors. The floor is open for a few questions. We have 3 minutes left, maybe one question.
I have a question.
Sure.
Nice, very nice talk on this. Thank you. In your decomposition, I don't know if I caught it correctly, but it seemed like some of your fragments had negative exchange repulsion. Did I see that right?
Right. Yes. Yes.
But polyrepulsion is positive definite, right?
Exchange repulsion.
Uh-huh.
Right.
It should be a repulsive interaction, right?
Right.
Perhaps it would be interesting to find out what was going on there.
Yeah, I will take a look at that. Yeah, thanks.
Let me say a few words. I think this is a bug in a script, I'm afraid. Andre just finished developing this, kind of finalizing the scripts a few days ago, and this is the first test.
Oh, so fresh results.
When we remove the so the exchange repulsion should be of course repulsive positive. So when we remove the caps from the fragments, we also remove some of the associated parameters for exchange repulsion.
Cool. Okay.
And, this is really quite tricky because we need to clean the localized wave function and the corresponding basis set. And so
it's not trivial. Yeah.
Yes, in our previous work, we really on kind of related thing, but not we saw that exchange repulsion remains positive and really compares quite nicely with SEP decomposition. But here, I'm afraid that this is just
Yeah, an artifact of the capping. Yeah,
it's sort of. I think I'm afraid it's a bug in the capping. And, yeah.
Got it. Okay, thank you. Yeah, this is really cool. This composition is very cool.
That kind of segues into a question I wanted to ask, which is, this workflow that involves stringing together like 10 different Python scripts seems really fragile to me, and so I'm wondering if you have any plans to combine this into a proper piece of software where I could just run one third-party program to connect the MM to the QM code and not,
that will be
individual scripts.
Yeah, I guess that will be the end goal. And we will explore different, we will try to use this whole setup in other protein ligand receptors, and just to see what happens with the code. And once we are sure it works, we will try to do that. Yeah.
Because I think if I could, at the risk of broadly caricaturing an entire field, sometimes in the biomolecular community, people get they treat their workflows as sacrosanct, and they're unwilling to make any modifications. And I think a large part of that is because very often they are stringing together multiple different programs, and any small tweak to one of them can break the whole workflow. And so to the extent that you can sort of have fewer moving parts, then you're better positioned to be able to turn the knobs on different codes without seeing the whole house of Python cards collapse.
Right. Yeah, I think that's the plan. But for now, yeah, we had previously done study of proteins, but they were not system specific. They were system specific, sorry. So now we're trying to make, like you said, we're trying to generalize it to any protein. And we'll definitely look at that.
I've had experiences in peer review where you ask the authors to change, one thing about their QM calculation to test something, and they're like, oh, we can't possibly do that because it will print out the wrong number of digits, and then this script won't work, and et cetera, et cetera. And yeah, anyway, thanks.
Thank you.
It was a nice talk.
Thank you.